everyone. I'm glad here today to introduce Oscar Dabrowski here, a truly passionate academic. Oscar obtained a bachelor degree in IT, specializing in software and complex systems at the Geneva School in Geneva. He then pursued an academic with a master's degree in computer science at the University of Geneva. During his master's, Oscar delved into image processing and developed an algorithm for automatic identification of pharmaceutical packaging. In 2019, he joined the research group of Professor François Rosera at the CIBM MRI section, joined PhD project with Professor Bastien Chopard from the Department of Computer Science at the University of Geneva. And today, Oscar will take us on a deep dive into the case space, showcasing a project on retrospective motion correction. And for the people in your room, I can reassure you, even the system is experimental, there is absolutely no risk of accidental, unexpected implosion during the dive.
Thank you very much for your introduction. So my talk is about estimating motion parameters in K-space, so we can then restore motion corrupted MRI scans, and we focus on MRI brain scans. So I will start by describing the motivations and objectives of my thesis, and then I will describe the methods we used, in particular the deep learning based approaches, and I will present experimental results we obtained in simulations as well as in vivo. So it is well known that MRI is very sensitive to motion, and despite many improvements over the years by, for example, reducing scan times with faster pulse sequences, or the many different prospective as well as retrospective motion correction algorithms, motion still remains a significant problem and no universal solution exists. And you can see here, it's a slice, motion corrupted slice of a 2D T1 weighted classical spin echo acquisition, a multi-slice. And so it suffers from motion. And we focus specifically on these types of acquisitions, which are very common in the clinical setting for pre and post gadolinium uptake. And the model of in-plane rigid body motion is well adapted. It makes sense for these types of acquisitions. And so the main idea here is that motion is embedded in K-space, and we'll try to, so the objective is to extract this motion from the K-space. So, as I mentioned, so information is embedded, motion information is embedded in K-space, and its effects are predictable thanks to the Fourier shift and rotation theorems, although some part of this motion may not be recoverable. And it makes sense to work in K-space rather than image space, because motion is very well localized in K-space as opposed to image space, where it's distributed everywhere in image space. And you can think, for example, of Cartesian classical 2D spin echo, for example, Cartesian acquisition, where the scanner acquires each line of K-space sequentially at each TR, each phase encoding line, and when the patient moves, for example, if the patient moves at some point, so the lines that the scanner is currently sampling will be affected by motion. And we chose to use deep neural networks to estimate motion, but we do not want to rely too much on black box, too much of a black box system. So for the correction, restoring removing the motion, we used a model-based approach to avoid what is sometimes called deep hallucinations. And now, so on this slide, I just wanted to give you an overview of the presentation, and we will then look under the hood of each of these components. And the first one here in this box, it's called, which we refer to as SHOCO, for choreography controlled motion. So this was in fact a sub-project of the main thesis, and its purpose is twofold. It's to create motion-free in vivo acquisitions, which we can then use to simulate motion, since deep learning models require very large amount of motion, so it's not practically feasible to have only in vivo training sets. So for training set, we simulate it on these motion-free acquisitions, and the other usage of this is to create motion-controlled in vivo test sets to assess the generalization performance of these deep learning models. And so once we have trained these models, we then correct the motion using a model-based approach based on the NUFT, which stands for non-uniform fast Fourier transform. Now let us first have a look inside this SHOCO box, if I may say. The idea is that subjects go inside the MRI scanner, and they are presented visual stimulus on a screen with a moving dot, and they are wearing glasses that restrict the field of view, so so as to avoid eye tracking. So the first step of this protocol is to perform an EPI acquisition. So you have these EPI time series, which have two purposes. One is for the subject to get used to be trained to reproduce the motion patterns accurately. So we show them repeatedly the same motion pattern over a period of about 5-6 minutes. And the other usage of this is that we perform rigid body motion registration to obtain empirical EPI labels, so empirical motion labels for the anatomical scans that are the concrete data that we acquired, this 2D classical spin echo. You can see an example here with the representative motion artifacts, these typical ringing artifacts that we obtain, and the corresponding K-space magnitude here. And so please notice these, observe these dark bands in K-space, and you can see they correspond to the motion onset, and the timing matches the EPI, so the empirical labels we have here. And so as a byproduct of this sub project, SHOCO, we developed a little algorithm to which we use as a K-space quality metric, in fact, thanks to these lines in K-space, which come from reconstruction with the eSpirit algorithm, because we take the raw data, multi-core data, and we reconstruct it, and we obtain the K-spaces like this with the appearance of these bands, and we can detect them using, here you can see the formula for the LP norm. We just take the logarithm of each line and we compute a norm, and then with traditional signal processing methods, smoothing, discrete derivatives, and thresholding, we're able to give a score to an acquisition. And so this allows us to identify motion-corrupted acquisitions from motion-free acquisitions, which we use for simulations. And so here is the mathematical description of the rigid body in plane, 2D in plane motion. And this slide may seem a bit heavy or technical, but just the message here is to remember is that the center of rotation is not necessarily, and in practice, not the ideal rotation center that would be at the center of the field of view. It's rather shifted somewhere. And these results, so to say, a non-ideal center of rotation results in residual translations which need to be corrected. So it's not a pure rotation. We have the associated translations, and we have these, so the center of rotation and these which I refer to Tx and Ty, the residual translations, and of course the angle of rotation. And these distributions here, we chose them according to what we observed in the EPI parameters in vivo. That's the thanks to this ROCO protocol. And so the neural network, the goal of this the neural network is to estimate these free motion parameters, angle Tx and Ty, so we can then correct the motion. And so now this is the model we used. So it's very similar to a LearnNet style convolutional neural network, which was interestingly was used first for the recognition of handwritten digits, so in image space, and it's interesting to see that it works also in K-space, and it has so what is referred traditionally as a feature extractor block. So the input is fed to the neural network, and it undergoes a series of convolutions. And in the end, we have what is sometimes interpreted as a classifier, but here it's rather a regression problem because we predict these three real values, angle Tx and Ty. And the key aspect of this model is that it's referenceless. It only uses local information to predict motion. So we give it as input narrow window, narrow neighborhood around the region of motion. So in our experiments, we use one motion event, and we give a narrow region around it, and the network must use only this information to predict these three motion parameters here. And now, given the estimation of these parameters, we can correct the motion, and we build the non-uniform Fourier matrix here, and you can see it's schematically represented by these red dots, these points, and so to give what I like to think about it as like in a reversed way, like if the patient was not moving, was staying still in the scanner, but that the scanner was sampling the wrong basis vectors, distorted Fourier basis vectors, as opposed to what happens in reality is that the patient is, of course, moving and the scanner is sampling the regular basis vectors. So the idea is that we distort the basis vectors according to the motion trajectory. And the first step actually is to remove the phase, because as we mentioned, there are residual translations which need to be removed, and this is related to the Fourier shift theorem. And once these phase ramps are removed, then we just apply the NUFT to remove the rotation effect. And here you can see this was an in vivo acquired scan, and the corrected results here of one slice. And now let us have a look at the results. So as we mentioned, we have this K-space quality metric, and one problem we had, what we wanted to do was to determine the optimal threshold and the optimal norm, the optimal P norm value to use, if you remember the algorithm we mentioned before. And it turns out that the optimal point is here, and it corresponds to a P norm of 1/2. And it's, strictly speaking, mathematically, it's a quasi-norm because it's below 1, and it corresponds to true positive rates of about 90% and false positive rate of around 4%. And given this optimal norm and so threshold, we can plot the distribution of the data. And here I classified the the motion data in 3 categories. So the blue one is mostly very small or visually undetectable motion. The orange one is medium motion, and large motion in yellow. And we can see that using this optimal threshold for the p norm of 1/2, we're able to discriminate to some extent. And now for the motion quantification. So here, so these are the results after training the neural network. And if you look from the left to right, it's the best case, medium case, and the worst case. And it corresponds to increasing spatial frequencies. So above these plots, you can see the corresponding spatial frequency on which the network was trained. And as could be expected, as we go higher and higher, have higher spatial harmonics, the performance gets worse, but it's still acceptable and allows some amount of motion correction. And as for the results for the simulation, so here you can see, these are simulated. This is simulated slice. So we have motion-free reference on which we applied the rigid body simulation, and here's the corrected. So after the neural network predicted the motion parameters, we applied the NUFT and obtained this result, where almost all the artifacts are removed. And of course, so we have a true reference, so we can compute the PSNR and SSIM, which are some traditional image quality metrics. And you can see to the right the distribution for many more slices like this, with many different angles. And we can see that the distributions are well separated. And this is the PSNR in decibels, and for the SSIM, it looks like that. And now for the in vivo results. So these slices, so A and C, we zoomed on a region of the brain for 2 different subjects. We used the most similar slices, most anatomically similar slices for 2 different subjects that performed motion according to the Shoko protocol. It was around 3 degrees. And in B, you have the corrected version. So again, the neural network predicted the parameters. It was 1 motion event, predicted parameters, and we used these parameters to build the NUFT and correct the motion. And same for C and D. You can see that the artifacts are essentially reduced. There are some remaining artifacts, but it's significantly reduced. And here we show the PSNR and SSIM for the in vivo acquisitions. And of course, we don't have the true reference because it's not simulated. It's in vivo, but as the second step after GPI acquisitions of each of the Shoko protocol, we always perform a no motion-free scan where the patient stays still, and subsequently they produce the different motion patterns. So we have these reference motionless scans that we can use as a sort of a weak reference. And we see that even like that, it's correct. We are able to improve the PSNR and SSIM in most of the cases, but there are some situations, the red lines are when the PSNR has actually decreased or stayed the same. But it comes from either failure of the neural net to estimate parameters, or also from this non-ideal reference. And so now to conclude, so we have presented this referenceless model that's able to learn anywhere in K-space. And so, as we mentioned, we wanted to avoid too much of a black box system. So we use motion model-based motion correction. And we also proposed this K-space metric as a byproduct of the Shoko project, which we propose as a sub-project, which we needed to generate data. And it's actually interesting because we did not find any K-space metric. They're usually always as far as we know, image space metrics. And so for the future work, we would like to implement the complete pipeline, and there still remains a lot of work to do. And for example, exploring multiple motion events and unconstrained motion, uncontrolled motion, free motion, free motion trajectories, and also leveraging single coils. Because we have used here e-spirit reconstructed coils, reconstructions from all the coils, e-spirit reconstructions, and would also like to move to 3D. And we think that this project has a great potential to, if it comes to an implementation, to reduce the scan times. To reduce the so that we can avoid rescanning due to motion correction. Ideally we can correct the motion and avoid rescanning and losing time, and therefore improving the costs and so on. Thank you very much, my supervisors, and thank you for this opportunity. And
yeah, thanks for the very nice presentation. I was wondering, based on the last point that you raised, how long does it take now? So once you've trained your algorithm, essentially applying it takes very short time.
Yes.
So is it something that could be implemented at the console, for example, that this image could be corrected and the MR tech could decide, okay, we still have to redo the scan, or it's good enough now with the motion correction?
Yes, absolutely. That would be an option, because what takes really a very long time is training these neural network models, and the inference, as it's called, sometimes to obtain a prediction is very fast. It's the order of less than a second. For one, I haven't computed the exact time, but it's very fast, and the NUFT is actually fast also, thanks to this Jeffrey Fessler toolbox, which.
And so you think the trained model is generalizable enough that you could apply it to any patient that is scanned and it would still work reasonably well?
Not as it is here. It's really a proof of concept, and it's focused on the spin echo, classical spin echo acquisitions, which actually we've seen. I was acquiring also sequences on the clinical scans to have additional data, motion-free data to simulate, as well as the Shoko. And I noticed that there are very high amount of motion-corrected acquisitions. And but to go back to your question, I think it can be generalized, but again, not as it is now. But we have to study the different motion trajectories and so on. But I think there is potential. But.
And I see Joe raised his hand, but I just have one more question. Sorry. So how does this work with acceleration? So under sample data, do you first reconstruct the image using the coil sensitivities, and then you Fourier transform back to have some kind of full K-space, or?
I think you're. So actually, we did not use acceleration here. Okay. It's the coils are full. It's the full data. So if acceleration were used, so I think you're referring maybe to if, for example, we acquired only half of the lines, something like that. So we would need to study what happens. So if we reconstruct with grapha or sense, it will introduce some artifacts due to the interpolation, and we will need to study that situation. But I think it will probably not network as is. We could try because it has I mean, we give a neighborhood around the region of motion onset. So we could try to pad it with zeros and see how it behaves. It's able to leverage the information that's there. But otherwise, we would need to study and probably to train the neural network to account for that, or at least we need to study or do, for example, a grappa, machine learning enhanced grappa or something like that.
Thank you.
Yeah, Joao, I think.
Yes, thank you. Didn't want to rush, Eliana. It's a very nice presentation. I just had a question. Looking at your motion artifacts, it seems they're dominated by ringing, as you showed quite well and you explained. I was wondering, because we also sometimes have just Gibbs ringing artifacts, even in images that did not have a lot of motion, simply because we didn't sample farther enough in K-space to sample these sharp transitions well enough. I was wondering how your networks might react to seeing Gibbs ringing artifacts that aren't due to motion, if you've looked into that.
Well, there are actually, I see them all the time, these Gibbs ringing artifacts, and they are there. I think probably, I'm not sure, but it's possible that these are Gibbs ringing artifacts. They are there, so the network sees them, but they are not taken into account. They are considered, in a sense, as part of the image. So the network doesn't try to correct them in particular, but yeah, we haven't specifically looked into that.
Okay, but at least it doesn't get misled into thinking it's motion.
No,
okay.
It works well with that.
Okay, but yeah, I guess as a suggestion, you could simulate it and see the effects. Yes, more systematically if you wish. In that sense, but otherwise, yeah, it's really nice work, and I think it's a really important thing to look into for these imaging applications. One other question: you use the V-Spirit, since you now, based on the discussion with Eliana, you mentioned there's no acceleration, so you're using it just to get the underlying image from all the coil combination.
Yes, exactly. Yes.
Okay.
It's the sum of square. You know, I use the coil profiles, so it's a pointwise multiplication by the coil profiles estimated by V-Spirit, and then there's a formula with a sum of squares, something like this, to reconstruct the final slice from all the coils. And in the training set, we have multiple different amount of coils. It ranges from 16 to about, I think, 58. So it's just 64 channel, but with 68 coils, for example, all range of different amount of coils.
But you do not need the phase in the end, no? You just stick to the magnitude, or I mean, for your end data.
No, I use the full complex data, because
I mean for your output, the image you want to have at the end.
You mean the corrected image?
Yeah, the output. I guess you just care about the magnitude in the end.
Well, I show the magnitude, but I can have the complex part. I can have the phase as well, but we did not look at it specifically, but we could have it if we wanted to.
Okay, yeah, that could be an advantage for phase applications.
Oh, we could.
QSM and so on. Yeah. So thank you very much.
Thank you, Oscar.